processes occurring in our brain, to the extent that in the 60s, leading scientists of artificial intelligence at MIT, they thought they can solve the problem of machine intelligence within one summer project. Today, after more than half century of exhaustive theoretical and empirical research, we know how unrealistic this view has been. The complexities involved in the visual information processing has demanded more than 2/3 of the neurons in our brain. This complexity is also manifested in our best computational model, convolutional neural networks that require more than 100 millions of parameters to only solve one specific task. Our rich sense of vision hasn't been achieved overnight. The biological vision goes back to more than 500 million years ago, and it has been proposed by some scientists, for example, Andrew Parker, as the leading cause of the Cambrian explosion when most major animals started to appear. That's why I'm strongly convinced in order to solve the challenging problem of machine intelligence, we require insight and collaboration from at least 3 different disciplines: neuro, cognitive, and computer sciences, that they all work on the problem of vision intelligence just from distinct perspectives. This has been the rationale behind my PhD project. Despite our great progress as a community in computer vision, today, biological vision remains vastly superior in comparison to the best we can achieve with the machine vision. The reasons for that can be discussed in detail. However, a picture is worth 1,000 words. These are the 2 paintings by Cole Phillips, and a prominent artist from late 19th century is known for its fade-away techniques. Although the color of foreground or background are physically identical in his paintings, we have no difficulties in perceiving the boundaries between objects. Such cases are extremely ambiguous for machine vision. This suggests that our biological visual system encodes the visual information in a more abstract way, relying on more appropriate information. Before moving to the rest of the presentation, I will attempt to summarize our entire visual perception in one single slide. Our visual system consists of 2 functional components: the eye, which is analogous to a camera, and the visual cortex, which does all the complex image processing. When the light enters the eye, they are absorbed by the rod and cone photoreceptors at the back of the retina. Rods are primarily for the night vision, and our color vision is thanks to 3 different types of cones that they have their sensitivity function at different wavelength ranges. The cone outputs are combined in an antagonistic manner and sent through the lateral geniculate nucleus to the visual cortex, which is located at the back of the brain. The neurons of the primary visual cortex, the area V1, they are responsive to low-level visual features, such as orientation and spatial frequency. And as we go deeper inside the ventral pathway, the size of the receptive fields are enlarged approximately by a factor of 3. This way, the neurons in the higher cortical areas, they can pull relevant information from the lower ones in order to achieve selectivity to very specific concepts. For example, your grandmother face. One of the highest cortical areas involved in the process of object recognition is the visual area IT. Prominent works by Jim DiCarlo has showed that neural activity in this area can be interpreted as the feature descriptor for object recognition. They recorded from the neural activity of the neurons at IT of a macaque in vivo, simply feeding them to a typical machine learning algorithm, for example, SVM, as if they were, for example, sieved features. The learned classifier has been shown that can match the performance of a typical subject for the same task. With that, I'm going to move to the rest of my presentation by starting to discuss the importance of the scene illuminant. In our everyday experience, our visual system experiences a constant change in the source of light, yet we are often unaware of that because our visual perception somehow accounts for that. Metamerism. Metamerism is a concept in which 2 distinct reflectance spectra, they result into identical color under different type of illuminants. For example, we can see the reflectance spectra of these 2 petals. They are physically different. However, they look both identical on the street lamp to us. This can cause great challenges for our visual perception, and this is the subject of this section. I should mention that the content of this chapter has been presented in the conferences of VSS and ICVS. Scientifically, we know color of a surface is a product of 3 different elements: the source of light, the reflectance spectra of the object itself, color sensitivity function, which is in our case is the LMS cones, and in the case of the camera is the RGB sensors. So we can see in the top row the multiplication of these three different elements for two distinct reflectance spectra. They result into identical three stimulus values, and therefore they both appear orangish to us. For the very same pair under illumination of the tungsten light, they result into distinct three stimulus values, and therefore one of them appears more reddish to us. In this study, we are interested to study how frequent such metameric pairs are in the real-world scenarios, and when they mismatch, how big of a difference do they cause. In order to answer this question, we gathered more than 11,000 reflectance spectra from a wide range of objects. We studied them under 20 different sources of light. We simply compared each reflectance spectrum to all the others. This gives us about 64 million spectra pair comparisons, and we analyzed this under all different illuminant pair comparison, which is 351. And in order to decide whether a color pair is metameric or not, we use the CIE delta E 2000. To the benefit of time, I'll jump directly to the summary of the results. In this study, we extend the previous findings, suggesting that the metameric pairs are indeed infrequent in the real-world scenarios. On average, we see only 2 samples out of 10,000 to be metameric, with the upper bound of 6 samples. Problematic cases are even further rare. Only 8 samples out of 1,000,000 change their color difference value with 1 unit. And only 1 sample out of 1,000,000, they change the delta E with a 2-unit value. We also proposed a novel representation of the metamers through a multidimensional scaling. Multidimensional scaling is a means to visualize the similarity between different elements in a data set. Here we have projected the frequency of the metamers across different illuminants in an arbitrary 2-dimensional space. And we can see a nice pattern has emerged according to their color temperature. Those that they are connected through the dashed lines, they are the smooth natural illuminants. And then we can see from the top to the bottom, the color temperature increases. We see a similar patterns for the fluorescent lamps on top of the figures. This can allow us to predict for any new illuminant how frequent metameric pairs they would have under different scenarios. And with that, I'm going to move to the next section, color constancy. Color constancy is the phenomenon in which color of objects stays relatively constant to our eyes under different illuminant conditions. For example, here, the Rubik's Cube has been illuminated under 2 different lights of yellow and purplish. However, its tiles remains to us constant. For example, blue, yellow, red, blue, yellow, red. But if we extract these tiles out of the context and bring them up there, we can see the blue tile actually on the left is physically gray. The same way the yellow tile on the right is physically gray. This is a very challenging case for our visual perception, and it has very important implications. Imagine each time you were parking your car in different places, the color would change. That would be very, very confusing. This is the subject of this section. I should mention the content of this section has been presented in the conferences of VSS and VMVC and has been recently published in PAMI. As discussed in the previous section, the color of the surface is a product of 3 different elements: the source of light, the reflectance spectra of the object itself, and the camera or the observer. Assuming that we know the color sensitivity function of the observer or the camera, an assumption which is easily violated with the images obtained from the internet or from the standard typical cameras, we still have 1 equation and 2 unknowns. This suggests mathematically it's impossible to disentangle the source of light from the surface of the object. Computational color constancy, they are categorized in general on 2 groups. The first is the learning-based methods, which they rely on machine learning algorithms. The second group relies on low-level features, assuming there are some intrinsic properties in an image which can hint towards the source of the light. For example, the famous grayscale algorithm assumes the sum of all the hues in an image is equivalent to the color gray. A subset of these groups is based on the difference of the Gaussian that resembles the shape of a typical receptive field in the visual cortex. There are 2 major challenges with the difference of a Gaussian formulation. The first is how to set the size of the Gaussian width, and the second is how to set the contribution of the surround to the center, the contribution of the larger Gaussian to the smaller Gaussian. Here we propose a solution for this problem. This is the flowchart of our model. The color the color biased image is convolved with our contrast variant difference of a Gaussian. The V1 output is pulled by larger V4 receptive fields. The scene illuminant is estimated, and the image is corrected. We are going to go through each section one by one. The V1 receptive fields. Physiological studies has been demonstrated that the behavior of the receptive fields all over the visual cortex is modulated by the contrast of the stimuli. In this figure, we can see neuronal activity of one specific neuron from macaque in vivo as a function of the grating radius. The only difference between the black and the gray curve is the contrast of the stimuli, with the black curve being exposed to a high contrast and the gray being exposed to a low contrast. We can see for both curves, they increase their activity up to this shaded gray area. In the shaded gray area, the black curve sees the suppression, whereas the gray one sees facilitation. And outside of the gray area, both of them see inhibition. So if we map that to this schematic view of the receptive field on the right, we can say that the part in the center is always facilitatory, always assume a positive weight. The part in the surround is always inhibitory, always assume a negative sign. And the part in the dual role, it changes according to the contrast of the stimuli. It can assume both positive and negative weights. We simply model that to our difference of the Gaussian. In our model, at every single pixel, a Gaussian is computed according to the local contrast of that pixel. Here I'm showing you for the center with the blue and the green curves, the extremals of the high and the low contrast Gaussians. And for any other pixel, it would assume a Gaussian between those two automatically according to its contrast. Physiologically, also, we know the contribution of the surround to the center is also modulated by its contrast. And that's why we can see the surround at high contrast has stronger inhibition, the red curve, and the surround at low contrast, the black curve, it has a smaller inhibition. This way, we have addressed two of the issues that we raised by the difference of a Gaussian formulation. If we convolve our image with this contrast adaptive difference of a Gaussian, the output has enhanced the edges if you pay attention to the borders of the color patches and the specularities down there. And also, it has suppressed the uniform areas if you pay attention, for example, to the middle of all those color patches. The output of V1 is pulled by larger receptive fields at V4. Previously, typically in the literature, people have used the max pooling in order to pull between different layers of the brain. Another proposal by Ebner that proposed a top X percentage pooling. For example, let's pull the top 5%, top 10%. But the problem is, how do you set that value X? Here we propose a solution based on the visual cortex of the cat, which suggests also the pooling mechanism is contrast modulated, pulling over a larger region at low contrast and pulling over a smaller region at high contrast. In this schematic, I'm trying to explain this phenomenon. For this arbitrary signal, we can see that the value of the max pooling, the red asterisk, is identical. Although the signal on the left, it has a high contrast, and the signal on the right, it has a low contrast. Max pooling only relies on the peak of the function, therefore it doesn't care about the contrast within it. However, in our formulation, we pull over a smaller region on the left because the contrast is higher, and we pull over a larger region on the right because the contrast is smaller. The output of V4 gives us estimated illuminant, which is basically a vector of the three elements. And then we can correct this biased image by dividing it by this vector to achieve this color-corrected image. We conducted experiments on 4 different data sets, 3 of them being single illuminants, 1 of them being multi-illuminant. And we evaluated it based on the 2 standard evaluation of the recovery and reproduction angular error. Here are example images from each of those data sets: SFU lab, gray board, color checker, and the multi-illuminant. And the values on the bottom right corner of each image is the reproduction angular errors. We can see that our model can predict fairly good in the synthetic images, in the natural daylight, in the dim evening, and also in the multi-illuminant scenes. Quantitatively speaking as well, we outperform all the other models, including learning-based methods, in the SFU lab datasets. In the other 3 different data sets, we perform better than the non-learning algorithms, and our results are comparable to the learning-based methods. And I should emphasize that we did not change the parameters of our model across different data sets. So we use the fixed set of parameters across all different data sets, which is not true for our competitors. We also analyze the contribution of different components of our model, namely the constant versus adaptive center, constant versus adaptive surround, constant versus adaptive pooling. To the benefit of time, I'm not going to the details of the results, but without any exceptions, in all the cases, the adaptive formulation improved the results. And also, we replaced the max pooling stage of 4 different color constancy algorithm, namely white patch, the first and second order, gray edge, and double apponency. So we simply remove the max pooling, and then we put our contrast value and pooling mechanism. And again, in all cases, without any exception, even in testing it on different parameters of these models, we can see the contrast variant pooling can improve those results. With that, I would like to close this section. So we saw a biologically model of the color constancy. We proposed the contrast adaptive kernels, which enhance the edges and specularities while suppressing the uniform regions. We proposed the generic contrast variant pooling mechanism that can pull informative edges while suppressing uninformative ones. And we show that our results are competitive to a state of the art. As a future work, we think it's important to account for some occasional facilitation of the surround. This way, we allow that our model oscillates between difference and sum of the Gaussian. Now that we have discussed about the illuminant of a scene, we can move to the next stage, which is how do we assign color names to different objects. The electromagnetic spectrum of light, when it enters our eyes, is continuous. Yet, for example, we see the rainbow clearly as 6 or 7 different color categories. So how do we achieve that? This is the subject of this section. I should mention the content of this section has been presented in the conference of ECVP and has been published in the Journal of +1. The initial works for the color naming goes back probably to 60 years ago when Berlin and Kay, they did a very influential psychophysical experiment. They basically gave each of these Munsell chips to the people from different languages across different cultures, more than hundreds of them. And the task for the subjects was to assign a color label to those. The finding was suggesting that there are 11 color categories that they are universal across different languages and cultures. Psychophysical experiments of nonverbal color categorization also has revealed that there should be some mechanism which goes through the underlying of the color categorization that is independent of the language and culture. The computational color categorizations, primarily they try to fit the parameters of their model to different psychophysical data. For example, the fuzzy models, they try to fit the parameters of their model to the data of the Berlin and K. Seaborn later proposed the K-means, and then later on we saw a triple sigma parameter model. Up to this point, all of them, they're fitting their data to the psychophysical data. However, there was a new model proposed suggesting that we can learn the color categories from the images, from the real-world images directly through the probabilistic latent semantic indexing. Our model is fundamentally different from all the others because in our model, the color categories, they are governed by the simple geometrical shapes. And then we partition the color space through simple ellipsoids. Physiological studies has shown a subset of the neurons in the V1, when they have been exposed to the color patches, they are responsive to a form of an ellipsoid shape in a color opponent space. We also saw such similar shapes in our psychophysical experiments of the color naming, which the subjects had to mark the border between two neighboring color. So we simply modeled each color category through one simple ellipsoidal. Each ellipsoid consists of 9 parameters, 3 of them being the center, 3 being the axis of the ellipsoid, and the other 3 is for the rotation across each axis. Here we can see 2 views of those ellipsoids, in the LAV color space. Our model is so simple that you can simply draw the ellipsoid, and then you have a running model that you can try it on. But in our experiments, we obtained the parameters of model through two different mechanisms. In the first case, we fit the parameters of each ellipsoid to the segmented color images of the eBay dataset. And in the second case, we average those results with our psychophysical experiments of the color frontiers. We conducted experiments at 3 different benchmark datasets. The first one, Munsell color chart. They are isolated pixels, and the other 2, they are real-world images. And we evaluated based on the true positive ratio. Here are our results on the Munsell color chart. On the top, we can see the result of our model that has been learned based on the real-world images, and in the bottom, the model that has been a combination of both psychophysical and real-world images. And the black crosses are our mismatches between the Berlin and Kagran, Truth and Sturgis and Whitefield and our model. We can see the model down there, which has been learned based on the psychophysical data, has lower number of the mismatches in comparison to the real-world data. And the biggest difference is on the top row, which is basically the frontier between the white color and all the chromatic colors. Quantitatively, we can see our model that has been learned based on the real-world images outperforms all the other models in the state of the art. However, I would like to put a stronger emphasis on the model that has been learned based on the combination of both psychophysical data and real-world images, because it can obtain almost perfect results for the Munsell chart, which is basically their isolated pixels. And then its results comparing to all the rest is comparable or even better. So this way, this model can explain both psychophysical data and real-world images. This is a qualitative results of our model on one sample image. This is the original image, our results based on 11 color categories, and our results on 12 different categories. And here are the heat map of each different color categories. So here we are also trying to show that it's very simple to learn a new color category in our model. So we basically learned the color cream based on only 2 sample images, nothing more than that. So if we categorize based on 11 categories, we can see those pixels at the back of the wall. They are categorized by mistake as a pink color. However, in the pink, if we look at it, the probability is not very high. So the reason this has been caused is because basically we didn't have a concept of color. So there are some intermediary colors that we might require to include in any color categorization model. So if we add the color cream, we can see in the heat map it has a very high probability. In the case of the 12 categories, they are correctly classified as a color cream. With that, I would like to close this section. We proposed a biologically inspired model of color naming. Our model is very simple through simple ellipsoidal shapes. This allows it to do a very straightforward fitting, and it makes it very easy to add any new color terms. And our model, unlike most other algorithms, can explain both psychophysical and real-world images. In the future work, we think it's very important to convert those ellipses to three-dimensional Gaussians, because this way it allows us to use the same center-surround mechanism, this is contrast variant models that we explained in the previous section of the color constancy, to use it here. And then probably this way we can explain different phenomena such as assimilation. With that, I'm going to move to the last section of this presentation. The question that we are investigating in this section is how do we separate objects from each other? I should mention the content of this chapter has been presented in the conferences of BMVC and ECVP, and it's been recently published in International Journal of Computer Vision. Previous works on edge detection goes with the typical edge kernels like at Sobel and Canny that they have been cobbled with the entire image. However, such solutions, they are extremely noisy to textures. Although some solution has been proposed based on the local smoothing, but in general, in the real-world images, such convolutional kernels, they cannot obtain very good results. That's why learning-based methods had appeared that they extract relevant features from an image, feeding them to a typical machine learning algorithms. And more recently, the state of the art relies heavily on the deep learning algorithms. However, there are two major challenges with deep learning algorithms for edge detection. Firstly, it's computationally very expensive because at every single pixel, both in the testing and the training, you need to assign if whether a pixel is edge or not. And secondly, from a biologically point of view, there are no indications that detecting edges is an output of such a laborious learning mechanism. They have been rather proposed to be through the orientation selective neurons, which comes within our model, that they are rectified through the surround modulation, and then they are modulated through the shape feedback. This is the flowchart of our proposed model. The image at different chromatic channels, they are convolved with single opponent cells in the lateral geniculate nucleus. After that, the edges are detected to the orientation selective double opponent cells. We account for the surround modulation. The V1 output is pulled by the V2 signal, and then we also account for the shape feedback. So we are going to go through each section one by one. The color opponent cells. As we discussed before, the cone outputs are combined in an antagonistic manners before sending them to the visual cortex. So typically, you have the luminance channel, which is the sum of the red, green, and the blue channel. And then you have the red-green color opponency, which is the difference between the red and the green signal. And then you have the yellow-blue color opponency, which is the difference between the blue and the average of the red and green signal. There is typically, these color opponency cells, they are modeled through balanced single opponent cells, meaning the kappa R and kappa G, for example, they are equal, or kappa B and kappa RG, they are equal. However, they are second type of the cells that has been shown in the physiology that they combine the cone outputs in not in a balanced manner. So meaning, for example, the kappa R is not equal to kappa G, or the kappa for the blue, but the kappa for the yellow, they are not equal. So we accounted for both type of the cells. This means the output of all color opponent channels, they are 5 different channels. One is the luminance, 2 for the red-green, so balanced, unbalanced, red-green, and here balanced and unbalanced, yellow-blue. Each of these color opponent channels, they are convolved with our orientation selective cell. We model the orientation selective cells in the V1 as the first derivative of Gaussian, originally proposed by Kenny. So we simply convolve every single of those color opponent channels at 12 different orientations with this first derivative of the Gaussian. So you get such a heat maps of the orientations. And simply, mathematically, the results of the V1 receptive fields is the sum of the center response, which I just explained above, and the surround response, which I'm going to explain in the coming slides. But it's very important to pay attention to this term zeta here, which connects the relation between the center to the surround according to its contrast. It's the same concept that we saw in the color constancy chapter, that basically in a high contrast, you see more suppression, and in a low contrast, you see less suppression and occasional facilitation. We accounted for 4 different types of surrounds. Here in the black circle, I'm showing a receptive field that has this orientation selective vertically. The is orientation is along the preferred orientation of the cell. It's a very, very narrow region. And the orthogonal orientation is, again, is very narrow, but it's perpendicular to the preferred orientation of the cell. Full surround is an isotropical region, 5 times larger than the center. And the far surround that it comes from the inter-areal connections. We go through each of them. In the case of the iso and orthogonal orientation surround, physiological and psychophysical studies show that if along the main axis, if the center depicted here as the blue shares the same orientation as the surround, then you see facilitation, because you see the collinearity effect. Here you have the collinearity. If along the main axis, the center and surround, they have a perpendicular orientation, you see the blocking effect, and therefore you see inhibition. Along the second axis, if the stimuli in the surrounding have the orientation perpendicular to the center, you see facilitation, because you see a pop-out effect. And along the second axis, if the surround and the center, they have the same orientation, they are parallel to each other, you see inhibition. And we simply model each of these surround modulation through this E, which is basically an elongated Gaussian. And again, we accounted for this term zeta, which is the contrast adaptivity of the center to the surround. We see a similar story for the full surround. If the center depicted as blue shares the same orientation as the surround, you see inhibition. Whereas if they have a perpendicular orientation, you see a strong facilitation. We model the full surround with this term mu, which is basically average kernel, because the full surround has been proposed that is not orientation selective, it's isotropical. And again, we have this term zeta, which accounts for this contrast adaptive concept that we've been discussing. We model the far surround to a multi-scale pyramid of the images because we propose that they come from different interareal connections. And physiological studies shows that the further away you go from the center, the contribution of the far surround to the center is decreased. Therefore, in our formulation, we have this term S in the denominator, which is basically the distance of the far surround to the center. And again, we see this term zeta, which is the contrast adaptivity term. The output of V1 is pulled by the V2 receptive fields. As I explained before, receptive fields in the ventral pathway, they increase their size by a factor of 3. So therefore, the size of our V2 receptive fields is 3 times larger than the V1 receptive. If this is our hypothetical V1 receptive field, which has the preferred orientation in a vertical direction, the V2 cells, they pull it in orthogonal orientation to that. And then here also, we typically modeled it with a typical center-surround mechanism, the center being positive, the surrounds being negative, inhibitory. And here again, we accounted for the same concept of the contrast adaptation. So how we implemented it, first at every single pixel, we computed the preferred orientation of that pixel, the preferred orientation of that receptive field. Then we convolved, if we found theta, we convolved it with the perpendicular theta to that. And again, we have this term zeta here, which accounts for the contrast adaptivity. The output of V2 is sent back as a shape feedback to V1. So this process is processed one more time. So we had before 5 different single opponent channels. Now we have feedback. So the output of our model is basically the sum of every single of those channels. So basically the sum of all the single opponents plus the feedback channels. We conducted experiments on 4 benchmark data sets, 3 of them being chromatic images, 1 of them being only grayscale images. And we evaluated it on the standard harmonic mean based on the 3 criteria of the optimal scale per entire data set, or for image, and the average precision. Here are 1 example results for each of these data sets. The SFU Lab 300, 500, the multi-Q data sets, and the contour integration. The numbers on the right, they are the harmonic means. In general, we can see that our model, unlike, for example, the color constancy, it can suppress a lot of textures. But at the same time, unlike the sparse color constancy, we can keep the real edges. For example, if you pay attention to the borders of the bird to the background. However, they kill a lot of the true edges as well. Quantitatively, we perform better than unknown learning algorithms and all those that they are biologically inspired. And our result comparable with simple learning approaches. I have to say the result of our deep learning is about 6–7% better than us. Here, the GBP is the learning method. Our result is comparable in the chromatic images. And I have to mention again, same as our color constancy experiment, we did not change the parameters of our model across different data sets. So we kept it identical. This is not true, for example, for the case of the GBP across different data sets. And you can see the problem raises if you try it, for example, on the grayscale images. The performance of the GBP drops significantly. And almost in all data sets, we are better, for example, here 7%, 4%, and 4%. So our model, it can generalize to different data sets. However, some learning-based methods, they have difficulty to achieving this. We also analyze different components of our model. In the first experiments, we tried only the simple first derivative of Gaussian. In the second case, we only accounted for the V1 surround modulation. In the second case, we included the V2, but we didn't have the shape feedback. And in the last experiment, we excluded the far surround. So we are interested to know how much each of those components contribute in our model. Here we are seeing the results in the precision recall curve. And the black curve is the first derivative of Gaussian, nothing fancy there. So if we add our V1 surround modulation, we reach to this pink curve, we already see 4% improvement. So this V1 surround modulation improved the results 4%. If we add the V2 module, we get extra 2%, the red curve. And if we also account for the shape feedback, we get to the green curve, another 2 extra %. If we exclude the far surround, our results drops by 2%, the blue curve. So overall, this suggests different components of our model, they contribute about 1–2%, and the biggest being the V1 surround modulation, which accounted for 4% of our improvement. With that, I would like to close this section. We saw a biologically model of edge detection. We proposed 4 different types of surrounds. We accounted the same as our color constancy for this contrast variation of the surround modulation, which seems to enhance the edge strength. We modeled the higher areal cortical areas, the V2, that seems to play an important role in suppressing the textures. And also, we accounted for the shape feedback in our model. Overall, we saw that our results can perform much better than a state-of-the-art in non-learning algorithms while being competitive to the learning one as well. As a future works, we think it's important to consider more complex shape configurations. Those stories that I was saying about the configuration of the ISO and orthogonal orientation, in reality, they are more complex, and a better model can benefit from a more complex modulation of those. And also accounting for a V4 receptive fields that they pull the signal from the V2, and you really have a real shape representation. With that, I'm going to conclude my presentation. We studied metamers in this PhD in the real-world images. After that, we proposed an adaptive model of color constancy. Then we saw an ellipsoidal model of color categorization, and then at the end, we saw a dynamic model of edge detection. In conclusion, we saw that biologically inspired models can boost state-of-the-art in computer vision. We saw that contrast is a crucial factor in visual information processing, to the extent that actually it has been proposed that humans, we are more responsive to the contrast than to absolute illuminance. And we proposed a dynamic surround modulation that we tried it in the color constant edge detection, and our formulation allowed us with a fixed set of parameters to obtain good results across different data sets. And last but not least, the biologically inspired models allows us to better understand our very own visual perception. There are many lines of future works that can be continued after this PhD work. The obvious one is the integrating different parts. So do the color constancy first, then do the color categorization. The second would be combine the odd and even symmetric kernels in one unified framework. Because in the color constancy, we saw even symmetric V1 receptive fields. In the edge detection, we saw odd symmetric receptive fields. So if we could unify them, both types of cells have been seen in the physiological studies. So I think our model can benefit from that. We could incorporate other factors of the surround modulation. We only accounted for the contrast and orientation selectivity of those. However, there are modulation according to the spatial frequency and according to the phase. And probably the hottest topic of the computer vision right now is the deep learning approaches. So we are interested to see if our formulation, our adaptive formulation of the kernels can improve the results also in the convolutional neural networks. Because as of now, despite their great performance and 140 million parameters or so, at runtime, they are always identical for 2 different images. And we know this is not the case for our human visual perception. We adapt to different scenarios. So if we could try that on a deep learning, that would be very nice. With that, I would like to thank you for your attention.
Thank you. No, I have first just a very general question about color. Does the visual system of all animals use color?
No, I mean only those that, for example, dogs, they don't have a very good color perception, if they have at all anything. It depends, I guess, it depends on the number of cones you have. For example, fishes that they have like 4 or more number of cones, they have a more richer sense of color.
Okay, and can color itself be of use for object recognition?
If it can be used only as a single entity for the object recognition, I would hardly doubt that, because the edges or other information, they are more important. But there are numerous different studies in the psychophysical literature suggesting that when you add the color, the recognition, it gets much faster. And in extreme cases of, for example, the crowded scenes, the color plays an important role in detecting different objects. So I wouldn't call it as the most important entity. However, it plays a very important role.
I remember a discussion I had more than 20 years ago with a person working, with a scientist working in visual perception. At that time, he was the director of the Dutch Psychological Institute in Nijmegen. His name is Charles there. And actually, his claim was that color is not useful for object recognition. And then I gave him 2 counterexamples of my own experience. Like, we know the advertisements of the Coca-Cola brand include this combination of small white and very bright red color. So personally, I associate any image that I see, if I see somewhere a combination of these colors, I immediately, the Coca-Cola, concept pops up. And I also have another example of, in the image that you show here, for instance, the yellow and the green that we see there. So these are colors that are in the logo of one Dutch bank, the ABN AMRO Bank. And similarly, I remember that there is a building near my home where the tiles outside have some ornaments of that, and I always instinctively look for where the office of the bank is, though there is no office at all, and it has nothing to do with the bank. So eventually there is some connection, and probably color creates some bias in our expectation. But here you do not really, in this thesis, use color for object recognition. These are more or less low-level image stuff.
Exactly. The truth be said, the original idea was to try to continue the thesis to reach to the object recognition parts, but time didn't allow us to explore it. So.
Then about color constancy. Now on pages 33 and later 39 in your thesis, you also have this here in your presentation, this nice illustration with the Rubik cube. And then the claim is that,
we could get there.
Yes, and then the point is clear. And then, okay, how to take this into account? What is proposed is that one uses these color common channels, and a color common channel then would eliminate, some constant contribution by the illumination. In this case, I think on the left, the yellow light. It will be eliminated in the color form scheme. But the color frequency model that you are using subsequently, it also has some spatial extent. You're using Gaussian functions or other functions with limited spatial extent. Then, if this is the case, can one say that one should observe some effects near the boundaries where two regions of two different colors meet more strongly than in the interior? And this is what, and I remember that in one of your subsequent images when you illustrate the application, you see that what comes out in the interior is different from what is immediately at the boundary of the regions. But when I look myself onto the original image with the two Rubik cubes, for me, the tiles are perfectly homogeneous. You know, I don't see any difference between the interior and the boundaries of a tile.
The reason for that is this is like a hypothetical V1 output. So this is not what you would perceive in your brain as the image. This is just like some intermediate steps, and then after that you estimate the scene illuminant and then you correct the color image. So this is somewhere presumably in your primary visual cortex, but you don't have access to it to really have the consciousness over that. That would be the reason for that. However, the reason that you see this effect is basically different normalizations. So as you were saying, here you have a different normalization on the borders and the homogenic regions because of the contrast that has been imposed from the surrounding regions to it.
But you don't have any model, because psychologists, they have some models for filling in or spread in the interior of a region. You don't have such models here that would follow this stage of V1, so that ultimately you come to perception of a uniform color of the tile.
The reason that after this stage we did propose the V4 pooling to estimate the source of the light, because in computational color constancy the evaluation is based on that. But otherwise what we are proposing actually might be the correct way to go, because at every single pixel basically you can do a different pooling and then you can correct the image at different pixel or regional levels. So you continue this work on that. You don't estimate the illuminant. Because in computational color constancies, assumption is that let's estimate the illuminant and correct the image with that. But there are actually, from the physiological and psychophysical literature, this concept is debuted a lot. Some scientists, they argue that there is no such a thing as estimation of the illuminant within our cortex. It's just we do the proper normalizations till we reach the stage that the image is color constant to us.
The Rubik cubes that you show, well, indeed, in the right cube, I would still call a green tile a green tile. Then, okay, let's say the RGB or any other representation of the color in these pixels. Thus, let's say if we take a gray tile, and on the left and on the right, it of course has different RGB values, or L star, A star, B star values. But these values, these two sets or two triplets, do they still fit in the same ellipsoid of the ellipsoids that you showed us later?
In the case of the color categorization, no, because in our color categorization models, we are basically working with these physical real values. So that's why you have to account for the color constantly first, then you could do color categorization. Alternatively, we did some experiments that I didn't include it in the thesis itself and the presentation, is that you could adapt those ellipsoid models according to the gamma of the gamut of the pixels that you could see in an image. So you can achieve the color categorization and color constancy in one go. We had some preliminary results on that, but we didn't have the time to continue following on that. But that could be one way to solve the problem of color categorization and color constancy at the same time. Or alternatively, if we convert them to this three-dimensional Gaussian, then we could do these adaptations. And then probably then they would fit into those ellipsoids. Those not anymore ellipsoid, three-dimensional Gaussian.
If I consider these images separately, especially the right image, which is somehow more striking for me, and if I take this image and take all the colors that appear there, and then do clustering, I can say, okay, I have some values that, and then I take them with the volume in color space that they fill, and to that volume I apply discretization, and then based on the relative discretization I can say, oh, this region is green and this region is red, and of course this adaptivity will imply then that I will see green and yellow and red in the right image and similarly in the left image. But now, if I will take an image that is composed only of greenish things, and then looks, you don't have such an example here, and then I illuminate it with different shades of green, different hues of green, but everything green, and then I apply such a model that I take all the points in color space, and then I apply clustering and take 11 clusters and call one of them red, another yellow, magenta, green, and blue. But okay, I can do that, but will I still perceive then something that is green as red?
You will get arbitrary color categories, which I don't think perceptually would be very meaningful to you.
Sorry, if I may,
Sure.
you can continue with questions. I would suggest we go outside for 5 minutes. So, but then please take all your time for the
Muchas gracias, muy amable.
La presentación no usó.
Merci. Muy amable, merci.
Los cambios.
Hasta luego.
Cuidado con lo que dices.
Oh, sí.
Okay, so we continue.
Thank you. Where are the other guys? Especially all the girls.
I think because the director said 15 minutes, so maybe some people will come back.
Okay. But we continue, yes?
I think
I think we can continue.
Yeah.
Okay. Now there is one paper of yours that you cite. It has been submitted or probably already published. It's about constancy beyond the classical receptive field.
Yes.
It's under review.
No. It just was published like 2-3 weeks ago. Yeah.
Congratulations.
Thank you very much.
How would you define the classical receptive field?
The classical receptive field basically is just in the, if you want to formulate it as a difference of Gaussian, is well, physiologically speaking, they were arguing that anything outside of the surround, I don't know how many decades ago, doesn't do any modulation on the what is inside the center. So the spike activity of the receptive fields, they were always thinking that is only what is within what they call it as a minimum receptive field. So basically, in this like schematic, whatever is only projected to the center, that stimulates the receptive field, and that's what they call it classical receptive field. And anything which was outside of it, they basically neglected it.
Yeah, but when they started mapping receptive fields, of course, we have receptive fields of different type. Is this an oriented receptive field, or?
This type of contrast variant modulation, they are
here about grading from the work from Angelucci.
Yes, this is the review of many other works. Yes, these are orientation selective, but this contrast modulation has been shown in the non-orientation selective neurons as well.
Yeah, but I mean, there, how can you define the center? Because these classical receptive fields, they have different areas. At least for the receptive fields of simple cells, they have a center, which of course can be excitatory or inhibitory depending on the polarity of the stimulus. And then they have a surround, which has opposite, opposite influence. If the center is excitatory, the surround is inhibitory. So already the classical receptive field, or let's say the receptive fields as determined by the pioneers in this area, like for instance Hugo and Wiesel, they already have this concept of having the center and the surround. So therefore I would like to know more about what do you refer to as a classical receptive field.
You are completely right. In the evolution of the physiological studies, they had this term of the surround later on. But then they had only, in this like schematic, only center and surround. So center, as you were proposing, has always assumes in a facilitatory modulation, and the surround is always negative, it's always inhibitory. But then the different studies like this one, it shows that this part in the middle is not always inhibitory or always facilitatory. This depends on the contrast of the stimuli that you are projecting it. So regardless of what is your preferred orientation or preferred stimuli of a receptive field, then if you just change the contrast of that, it changes the behavior of that receptive field. And that is what in many studies they refer to it as a beyond classical receptive field. Actually, the term comes, the beyond classical receptive field, is the title of their article. So that's why we also chose that.
Well, I was asking this question of what meaning you assign to this, expression beyond the classical receptive field, because when I was working in this area of non-classical receptive field inhibition 10, 15 years ago, we got an understanding understanding of what the classical receptive field is by, this classical receptive field is this area that you of course model with the function, which you determine using a very simple isolated stimulus, like for orientation selected stimulus. This would be a small bar. And then you move it around and you find the areas where this bar has excitatory effect, and other regions where it has inhibitory effect. And then you have this characteristic appearance of so-called gabble receptive fields where you have excitatory lobes and inhibitory lobes, but they are defined as excitatory and inhibitory only with respect to this very simple image, isolated bar shown on a plain background. And then people or researchers used for many years this type of stimulus in order to map, the term that they were using, map receptive fields. Until later, somewhere in the mid-90s, end of the 90s, people made more serious work of that by showing more complex stimuli, like you first determine the classical receptive field, then put a bar there that excites the cell, and then you show other things in the surrounding, like a grating. And then they found out that then the area from which a stimulus can still have influence on the response of a neuron can be much bigger than this domain that was determined with the simple stimulus. And that mostly this effect is inhibitor. And this gave rise to this concept of non-classical receptive field inhibition or surround suppression. And then other people like David Field also claim that there is a facilitatory effect in the continuation of a stimulus. Okay, they made models of that. But this is my understanding of a classical receptive field. So here, in your picture there to the right, I would think that something that is in the center there, it would be a classical receptive field of a Gabor function, for instance, that includes not only excitatory effect but also inhibitory. I would put a small Gabor function there. This is my understanding. Therefore, my question of what exactly means beyond.
You are 100% is right. So in the typically then if the Gabor filter would be, because it would be very close to basically a second derivative of a Gaussian. So you basically have only the center and surround. So if you look at it from a different direction. But this beyond part comes from this dual role area that here in this case is modulated according to the contrast. So basically the Gabor filter that you are proposing, it would just change the size of its Gabor filter. That is the beyond part.
Yes, okay. This changes the size of, let's say, the extent of the Gabor filter.
Exactly, yes.
Yeah. Yeah, I remember I listened to one talk by Angelucci many years ago where she was making these claims and so on. Okay, so this work continues. Now, one more question. You started your presentation with two very nice artistic images, paintings by some artists.
Yes.
Yes. And, well, of course, in psychophysics, you have also much simpler images that illustrate the point of so-called illusionary contours. There are contours that, if you take a look at the contours, there is no contours there.